In this video, I'm going to go over the concept of R squared, or coefficient of determination, which are two terms referring to the same concept. Well, R squared is a performance metric for regression algorithms, but before I take a deep dive into the concept of R squared, let's refresh our memory about performance metrics for classification algorithms. That would help us to understand the differences between the two much better. So in classification, the machine learning algorithm either makes a correct or false classification, and therefore, based on the performance of the classification algorithm, we can create a confusion matrix and calculate measures of accuracy, recall, and precision. So remember, this could be a classification task. We here are tasked with classifying the images as either orange or apple. So basically the classification is to say whether it is an orange or not. We can construct a confusion matrix based on how the machine learning algorithm performs. In cases where it correctly classifies something that is actually an orange, as an orange, we would have a true positive. And in cases where it correctly classifies an apple as an apple, then we would have a true negative. Now, in cases where something is truly an orange, but it incorrectly classifies them to be an apple, then there you have a false negative. And similarly, where something is not an orange in reality, basically that is an apple, but the computer or the classification algorithm incorrectly classifies them to be an orange, then there you have a false positive. And then in the previous videos, which I'm going to link in the description below, you would see how we use this confusion matrix to calculate those measures of accuracy, recall, and precision. Now, in classification, what matters is if the machine is right or wrong, right? Whereas in regression, what matters is how close the machine is to the right answer. Think of it as a true and false question versus an essay in your exam. In true and false questions, you would either get the whole point or not, meaning that you either make the right choice or not. Whereas in essay question, you can get partial points, right? Depending on how close you are to the correct answer. In other words, in the true and false questions, it really doesn't matter whether you were 99% sure or whether you were 51% sure when you chose your answer. It is either true or false. I, as an instructor, wouldn't care how sure you were when you chose the answer in your true and false question. You will either get the whole points or 0 points for that true and false question, depending on how well you performed. Whereas in the essay question, you can get something between 0% of the whole points all the way to 100% of the whole points for that question. Now, another way to remember the concept of regression is to think about the game show, The Price is Right, right? There are multiple contestants who are competing in this show, and the task at hand is to guess what is the actual price of an item. All right. So think of these people who are competing with each other as machine learning algorithms, right? Each of them is going to come up with a prediction based on their training, right? That is the prediction of the machine learning algorithm. And then the winner is going to be the one who makes a prediction that is closest to the actual price of the item, right? Now, in the best case scenario, the person, or in this case, the machine learning algorithm, can make a prediction that is exactly and precisely the same value, the same actual price of the item, right? But it could also be the case that neither of these contestants can make the exactly right prediction. And in that case, the winner is going to be the one that makes a closer prediction, all right? So here, it really matters how close you are to the right answer, because even if you cannot make the exact prediction, if you're close enough or if you're closer than others, then you're going to win that game. Now, let's see how that concept applies in the regression. Well, we can define as r squared as the answer to the question that is asking how much of the variation in data can the model explain. Remember, this was the model that we were working with that was explaining the final grade of the students based on the number of hours that they had studied. And here we're talking about how much of the variation in data the model can explain. Well, let's see what variation basically means. Well, in order to calculate the variation, the very first thing that we do is that we take the average, and this is the average line, all right? We call it, or we show it by y hat, all right? This would be the average value of the grades of the students. Once we have the average value, we're going to calculate the distance between each grade and the average value. Basically, we're going to see how far off each grade is from the average, and once we calculate it, we square it and we add it up, right? That would be the variation from the mean. And if you pay attention, you would see that it is very close to the concept of variance, right? You would calculate the variance the same way, except the fact that there you would divide it by the total number of observations in your data set. So it is very close to the concept of variation, and the difference is that there is no denominator here, right? So once you calculate the difference from the mean, square it and add it up for all the observations, you would have the variation from the mean. Now, do you remember the concept of the sum of squared errors? Go back to the introduction to the OLS regression video, which I'm going to again post in the descriptions if you need a refresher on that. Sum of squared errors is basically a measure of the variation in the data that is not explained by the model, right? SSE was measuring how far off each point is from the predictions, right? And basically that is why the goal in the OLS is to find the line or the prediction that has the least sum of the square errors. Basically, you wanted to have a line that makes the least amount of errors. Now, with that concept, we can define the percentage of the total variation that is not explained by the model as the ratio between sum of squared errors and total variation. Again, note that the SSE is the variation in the data set that our model was not able to explain. Basically, that was the total error of our model, or the total things that the model could not explain. So if SSE divided by the total variation is the percentage of the variation that the model cannot explain, then the 1 minus SSE divided by the total variation would be the percentage of the variation that the model can explain, and that is the formula for R squared. A couple of points. R squared ranges between 0 and 1. The higher the R squared, the more explaining power the model has. Basically, your goal is to have a regression model that has an R squared of 1, which very rarely happens. But when you have multiple regression models, one measure that you can evaluate them is the R squared and see which one has a higher R squared. Now, at the extreme case where you have a data set in which the outcome is completely random. There is no relationship that you can determine between the feature and the outcome. You would have a case where the best guess that you can make is to say, oh, okay, the outcome is going to be equal to whatever the average is. All right. So think of it as an extreme scenario where the instructor just randomly gives grades to students without any consideration of how well they did in the exam or how much they studied or whatever. Okay, that would be a case where the relationship between the hours studied and the grades got is completely random. All right. And if you wanted to predict the grade of a student in that scenario, the best that you can make is say that, okay, what is the average of the grades given to the students? And the average is the best guess that I can have as the machine learning algorithm for the grade, for the predicted grade of a hypothetical student. And if you want to visualize it, this is going to be the prediction. And actually, if you run a regression on this randomly generated data, the regression line would be equal to the average of the outcome. All right. So what does it mean? If your prediction line, if your regression line is actually the average line, it means that the sum of the squared errors is actually the same thing as the total variation. Because remember, in the total variation, you would add up the differences between the actual points and the average line, right? Now, if the average line is your regression line, it means that the sum of the squared errors is also going to be equal to the total variation. And therefore, if you remember the formula of R square, where you had the SSE divided by total variation, now you would have total variation divided by total variation. So this part is going to be equal to 1, and therefore 1 minus 1 is going to be 0. Basically, here you have a model that can explain zero variation in the model. The model cannot explain why a student gets a particular grade, right? Think about it conceptually. If I were to give you grades completely randomly, then you would have no explanation of why you got 100 or why you got a 0, right? It's completely random, all right? That is where the R square of the model is going to be equal to 0. Now, in the other extreme case where every observation's outcome could be precisely determined by the feature, meaning that you could run a line that goes through every single point, then the sum of the squared errors would be equal to 0 because there is no error. And therefore, if you plug in to the formula of the R squared, the SSE here in the numerator is going to be 0. So 0 divided by whatever is the variation is going to be 0. And then 1 minus 0 is going to be 1. Here you have an R squared which is equal to 1 or 100%, meaning that you have a regression line that can explain without any errors the final outcome.